So we're going to get back into those 5 important things about VisIt, the 5 building blocks. So hopefully you had a chance to download VisIt. If you didn't, you can get to the links from this VisIt users website or from the slides. But again, we're going to be using VisIt 3.3.0, which is our latest release. And if you have problems opening it up and things like that, I can come around a little bit later and help you. But just try to get it up and running on your own. The plan again is I'm going to do some kind of a whirlwind tour of different features, and then we're going to kick back to this aneurysm tutorial and kind of do a more scripted tutorial with that. So let's get started. So once you have VisIt installed, it's a little bit different on different platforms, but I'm on a Mac, so I can just click on the DMG, the app from the DMG, and VisIt will pop up. And I'm going to share some stories about woes with Macs shortly, but let's get it going. So VisIt's loading up here. So the first thing you notice is you may see the window. This window over here looks blank. If you resize it a little bit, that will resolve that. So that was one of the sad things about Macs. Another sad thing, and something that we're working on fixing, is that over the years, Apple has gotten much more stricter about the things it allows all the applications to do. So we go through this very large process of asking it for permission and signing our code and all those things. But there's a couple things that we still haven't been able to iron out. And I want to show them to you and show you a workaround so you don't hit that problem if you're on a Mac. On Linux and Windows, you should be fine. You shouldn't have these issues. The problems that we have on Mac currently are when you go to open, even though I can browse my home directory, it's not going to let me go into my documents or my desktop. It's just going to yell at me and say, you don't have permission for that. So if you're running as I am, just don't download things on your desktop or documents. Put them somewhere else. The other thing you can do is if you have VisIt in your path, like I do here, so I added VisIt to my path, the main launcher. On the Mac, it'll be under the VisIt app, contents, resources, bin, VisIt. If that's in your path and you launch it, since your terminal has permissions for all these things likely, you'll be completely fine. So if you hit those things, apologize. We're still trying to figure out the right handshake we do with Mac people to say, please let us use these couple directories. All right, anyways, so here's VisIt. We got it up. We haven't done anything yet. I just want to describe a little bit. This column here on the left is the GUI, so that's where you're going to be driving things in terms of setting up plots. This on the right is the viewer, so that's where you're going to see stuff. Hidden to you are the engine, which you won't see, right? That's the piece behind the scenes that is going to be doing the processing. Let's get started here by opening up a sample data set. So that brings us to our first building block, which is a database. So I click Open, and I'm going to go down to where I have downloaded the example data sets. So those are linked on the wiki. We're going to be using something called example.silo. It's our favorite example. You should be able to find that in the main tutorial examples. Oops. All right. So I'm clicking on example.silo now, and I'm going to go ahead and open it. And then the first thing that you notice is that absolutely nothing happens. This is the same thing with ParaView, right? You kind of want to ask, it wants to ask you, do you really want to do something before it tries to go off and do computation? And that's really important when you're running on a big supercomputer. It might, some of the operations might take a little time, so you don't want it to just kind of guess what you're doing. So we're going to start by creating a plot. So plot's our second building block. That's how we make pictures. So I'm going to say add here, and this plus. And you see a list of all the different plotting, basically primitives that VisIt has here. The most common ones that you're going to want to use are pseudo-color plot and then also mesh plot. So let's do a pseudo-color plot first. So when I come down here and I go to pseudo-color, I see an additional menu. These are the variables that are inside this database that I opened, right? So they're the fields on that data. I'm going to make a plot of pressure. And okay, we're good. It's green here, but we still don't have a picture, right? It still wants you to be intentional. So we're going to click Draw. And when I click Draw, I now have our plot here on the right, the pseudo-color plot. Yours might look different for me because the default color table is different, but I'm going to show you how to change that in just a minute. If I come over here to the viewer, I can then interact with this. So this is a 3D data set that has a field interpolated on it. So I can scroll, I can zoom, all of those different things. So this is where you would set up, your views how you'd like it. If you make a mistake, you can get back to the default view with this camera that has basically a double backwards circle or double backwards arrows on it. So that will reset me to the default. And another helpful thing to know is if you've done several camera changes, there's a stack of cameras, and you can go back to the last one, with this, or you can go forward with this. So this helps you. But panic mode, you hit reset, and you're back to where you were at the beginning. Right. You can have multiple viewer windows. I'm not going to cover that. It'll clutter the screen, but it's possible to pull up 4 or 5 different windows and then link them and things like that. So keep that in mind, but I'm not going to cover that right now. So we're going to go back over here to our pseudo-color plot. I'm going to click on the arrow, and that expands the pipeline. So right now, all we're doing is we're plotting pressure, but once we start adding other things, there'll be other things you can adjust in here. So I'm going to double-click on pseudo-color, which is the end of our pipeline, and this is where we have the options for the plot that we can adjust. So you'll notice that I have a different color table. You can change your color table too. Another thing we can do here is we can change the limits of the data to change the way it's mapped. So if I look at this data set, the values go between 5 and 1, right? 5 being the maximum, almost 6, I guess, and 1 being the minimum. So if I wanted to pin the range to something different, I could. So say I wanted to only have my pseudo-color span 3 and 4, I could do that, and I get a very different picture. And then another thing you can do, which is nice, is if you wanted to visually identify the things that are outside of your range, you have options for that. So you can say use this color for everything below my minimum. So if I really wanted to point out where the minimum data was, I could choose a color that contrasts a lot, and I can kind of figure that out, right, where these things are. There'll be other ways to understand like isovolumes and contours, the structure of the data, but this is a simple way. All right. So I'm going to go ahead and I'm going to say panic. I'm going to go back to our original view, but I'll keep this color table dialed in. And I'm going to add another type of plot. So I'm going to add a mesh plot this time. So again, there's a list of meshes here, or a list of variables here. These happen to be the data sets that are in the file, so there's multiple meshes in the file. The one that we're looking at here is called mesh. So I'm just going to plot that. I have to hit draw. And now you'll see we have these combined plots, right? We have the pseudo-color and we have the mesh plot, and the mesh draws the lines of the mesh topology there. So now that we've got our plot that we've made, let's render it. So if I go to File, I can go to Set Save Options. And here I can say, hey, I'd like to render a PNG, get an image file out. And I can also override and say, well, I want it to be this big or what have you. So in this case, you can say, please use the screen ratio of whatever this picture is, but if you wanted to go crazy, you can make it much more higher resolution. So I can go ahead and say, please save this out at 4096. I hit save, and window down here, you couldn't see it because I'm covering it, but it says, hey, I saved this PNG. You can change the names and stuff, but let me just show you real quick. Let's go back here. So I rendered out that PNG, and it's shrinking it down. It's really actually higher resolution, but I rendered out that PNG, and that's how you can get your plots out. If you have a time-varying data set, there's a movie wizard that says, walk through my time steps and save a whole bunch of files. You can use that, and then you can encode it to like an MPEG or something like that. So let's come back here. Now I'm gonna play a trick here. Let's try to run on Cooley. So we'll see if it works, and we'll see if it doesn't. But the way you run on a remote system with this client-server mode is you have a set of host configurations that are installed. When you install VisIt, you might have skipped over it. Don't worry about that now. But when they're installed, I can show you how to do it later if you want to, you have a selection of systems that you want to connect to. So we have Argonne Cooley here as one of my options. So if I click this, oops, I have to actually click it. It's going to pop up, and it's going to say, hey, please give me your password. One thing is that my username on Cooley is not the same as my username on my laptop, so I have to fix that. So I'm going to say change username. My username on Cooley happens to be Harrison. And then it's going to ask me for my password again, so I'm going to use my token. I'm going to try to use my token. 5 more attempts to get it right. Okay, and I'm going to type it in here. Hit OK. It's going to wait a second, and then it's connected. And now you notice it says up here, hey, I'm on Cooley. And this happens to be, you know, the clutter of stuff that I have on my Cooley account. But I do happen to have some data here too. So I'm going to click here, and I'm going to open up this this data set here. Actually, I'll open up the example.silo, right? Because that's the same one you're looking at. So I happen to have it there on Cooley. I hit OK. And it's going to ask me, hey, how do you want to run? So VisIt will understand how to submit a batch job and all those things. I'm going to cheat now. I'm going to run serial. So it's just going to run on the login node. Normally you would click parallel, you would click your banks and all that stuff, but I'm just going to say OK here. It launches on Cooley, and now, well, we're back to kind of where we were before. I can go ahead and say I want to create a pseudo color plot of pressure, hit draw, and it'll take a little bit longer, mainly because I'm running over this Wi-Fi. But here we are, right? So we did the exact same thing, but now the engine is actually running on Cooley and the local parts are running here. How do I know that? How do you know I'm not lying? I could be lying, but I'm not. If we go to File, there's Compute Engines that shows you what's going on here, right? So if this was a parallel launch, it would say I'm using so many processors, et cetera. I can also kill the engine here, and then I'm at a state where I'm no longer using the Cooley resources. So I'm going to go ahead and close that, and we're just going to work locally from now on. All right, so databases, we got our data in. Plots, we're making pictures. So far, we're doing well, but we want to do more exciting things. Next thing is we want to add some operators. So I'm going to start by creating my plot again, my plot of pressure. And I'm going to go here to operators, and the operators are listed hierarchically. So these are like filters. These are things that you can use to transform your data. But they're grouped into different similar capabilities. So I'm going to be looking under slicing. So slicing has a couple different operators you can apply. The most commonly used ones are slice, 3-slice, and isosurface, which is a contour. But I'm going to start with a slice. So let's do slice. We're back to green. We click draw, and now I have a 2D data set that I got out of my 3D data set, right? There were some default options that were used here. Let's go ahead and take a look at the options by going over into the GUI and then double-clicking on slice there. We can see that, you know, it was selected to be x-axis or y-axis by default. If I wanted to do a different axis, I could change that. I could also change this, so if I wanted to still keep that 3D context, I could change it. I could say don't project it to 2D, and it'll keep it as a 3D data set, and then we can just interact with it here. But I'm going to go back to 2D quickly because I want to show you something else. So we can also do lineouts. It's easy to do a lineout on a 2D data set because you can just drag. For 3D, you can do that too, but typically people just put the endpoints into another place in our GUI because it's just easier for 3D for you to say exactly where you want it. But I'm just going to drag here. So I click the lineout, which is the red and blue squiggles up there at the top. And I start and I click on my plot and I drag it, and then you can see it pops up another window, another visualization window with that curve. You can save that curve out to a text file. There's things you can do with it. If you do multiple lineouts, it'll keep plotting them all in this window. I'm a little constrained for space here, but there's some examples of A and B. Other things you can do, interaction modes. There's a rubber band zoom, like a magnifying glass. I can use that to zoom way in on my data. There are pick modes. So if I wanted to find something out about a zone, or a cell or an element, depending on your nomenclature, I can use the zone pick in VisIt. That's what we call it. If I click this, I get an output that shows me everything it knows about where I just clicked. There's some other different options you can turn on that aren't by default, but what's useful here is, hey, you clicked at this point in space. This is actually a nodal data set, so it's associated with the vertices or the points. You can think about it that way. So it's showing you for that cell all of the values for that. So this is highly detailed debugging information that's very useful. Like if you have a mesh tangle, usually you're going in there and asking questions about this. So let's add an isosurface operator. So that's also under slicing. So an isosurface operator is effectively a contour. The difference between the isosurface operator that we're applying here and the contour plot is a little subtle, but the isosurface operator allows us to still plot another variable like pressure or something like that in a pseudo-color plot, whereas the contour just draws the contours and colors them individual colors. But oftentimes isosurface is very useful in what you would like. We're going to add that, and by default it's going to pull out, oops, I had my pick on. Let me go back to the normal mode, which is this navigation here. By default it's going to have some options just like we have here. I'm going to click on this, and by default what it's doing is it's picking 10 different equally spaced values to contour at. So when you think about doing contour, it's a level set method, or isosurface, it's a level set method. You're looking at specific, the surfaces at specific values. A little bit later we'll talk about isovolume, which looks at the isosurface, or basically the level sets that sweep between two values. But this is a method that extracts surfaces. If I wanted to do, default's fine, it's doing something, but if I know, hey, I really want to understand what's happening at a particular place or a particular value, I can type that in directly. So I could say, well, what's going on at 3? And I could say what's going on at 3 and 4, right? So I could get different ISO values there. You can also do percentages. Sometimes that's more intuitive if you'd like it to be at the 50% mark. Oops, there's nothing at that, I guess. Maybe it is really 50. Yeah, so it's a, let's see. There we go, 50% mark. So all of these operators have their own little windows when you click on them, and they have their own attributes. And they expose this also to you in Python, so you can do the same type of tweaks to these plots. So we have our isosurface here. Another thing we could do is say we're really happy with this isosurface and we want to save the data itself for later. We can export it. So if I go to File, under File there's Export Database. And there's a whole host of options that we can use here. We're going to export it to a VTK file in this case, so that's nice, although I clicked it wrong. Because a lot of tools can use VTK, right? There's other different options. We can go ahead and export the different variables that we want, but we can also add other ones if we wanted them. So if I hit Apply here and then I hit Export, there's some extra options because there's a lot of options that we could do with VTK. I'm just going to accept the default. And if I click down here, because it went by too fast, we can see that it told us that it exported something to this file name here. If I go back to my data set here, so there it is. So I'm just going to open up a new version of VisIt with that database real quick. So we can see that it exported just the pressure, and looks like I got I know what I did. Hold on a second. I opened the wrong file. Or maybe I didn't. Okay, well that's a surprise. So something went wrong there, but it should have been reflecting exactly what we had here. So I will have to file a bug ticket later. We can choose different formats. So there's also some ways to save, you can save things out to like CSV files and stuff like that, and it'll do some of the flattening for you. Still a little bit involved. We're trying to make it a little bit easier to do all those things. That's more common. But takeaway here is you can do some things like slice your data, and then you can have a reduced data set, right? And you can go through that and save it to a file and then just pull that up later, and all of your operations are baked in already. All right. So let's look at a couple other plots here. So I want to look at a volume plot. So this is a volume visualization. So that's sending rays through your data and applying a transfer function as those rays hit the different values in your data. So let's go ahead and do a volume plot of temperature. And I'm gonna just make this smaller so I can move around a little bit better here. So volume plots are really beautiful and really impactful. They also take a lot of time to set up and think about. And a lot of that is thinking about the transfer function. So the transfer function is what VisIt or similar tools are going to apply, how they're going to apply the color as these rays go through your data set. So in this particular picture here, we have a color table, which I'm going to change to something else. And then below here, you see a histogram of the data. That's the actual data there. And then you see this opacity ramp. You can go through here and you can basically squiggle a transfer function in to highlight different parts of your data. And as you do that and you hit apply, you'll get different pictures, right? So if you really want to hone in on a particular feature, you can cut out whole parts of this and you'll start to get different, different transfer functions will give you very different results. So I think when Joe talked about this, he talked about, well, for the mouse data, right? The bone density is different than other tissues, right? So you can think about your color table and putting together these transfer functions and spend a lot of time, but make some really impactful and beautiful visualizations with it. I want to show a filled boundary plot. So what is this all about? So VisIt supports multi-material data. So for simulations, usually ALE simulations, arbitrary Lagrangian or Eulerian simulations, they don't resolve all the finest details at the mesh level. They will actually resolve things at a sub-element level, and they will use volume fractions. I am 50% air and I am 50% water, right? So, or I am 0.1% of one material and all of these other 20 materials. I have parts of me in this cell. So VisIt has a material interface reconstruction algorithm. If you present that data to them, it will find those interfaces on the fly, and that's what this filled boundary plot does. So if I add filled boundary and I click mat, which is the name of our materials that happen to exist in this, and hit draw, we get a kind of a sad plot at first because there's not really much going on. But if I go here into this subset plot, this is where VisIt allows you to select different parts of your data, including materials. I have this hierarchy and I have my mat, and I'll see that I actually have two different materials here, air and chrome. And what we're seeing here is all air. Well, the reason why is because the chrome's on the inside. So if I unclick this and I hit apply, we get this funky looking ring, topologically sad ring that you probably wouldn't want to give to someone. They'd be confused. But you have this funky pattern right embedded in here. And vice versa, I could also turn off this chrome ring, but you're just gonna see the air all around, right? So let me turn it all back on. Another way you can look at this data is you could add a 3-slice. So a 3-slice will add 3 orthogonal slices to it. It is a really helpful way if you have a big volume and you just don't know what's going on inside. You can throw a 3-slice on and then you get a picture right away. So I'm gonna add that. That's under slicing. And it's at the bottom here, 3-slice. And I hit draw. And you'll see that we have, our part of our ring. We don't know it's a ring here because we just have these different slices of it. But we have part of our ring on these different three planes, and we can see where the material interface is, and it actually shows up here and saying, hey, that's chrome and that's air. You could change where the 3-slice parameters are, just like you can change anything else. Like if you wanted to move one of these planes over, you could, right? So, and you could animate those if you'd like to with the script. Okay, so we talked a lot about operators. Let's talk about expressions. So expressions are a way that VisIt provides you to derive quantities on the fly. The best example I like to talk about for this is assume that you published, say, density, but you really wanted to know the mass of your data set, right, or of part of your data. So if I have density, and I multiply that by the volume of each cell, I'll have my mass per element, right? So VisIt can calculate the volume for you. You have the density, you put the two together, you're in good shape. You can even integrate it, right? Another common thing that people want to do is take magnitudes of vector fields, and VisIt actually does that, creates expressions that automatically do that for you. Or maybe take a gradient, right? So you put something into a gradient, and you're going to get a vector field out. That's the example I'm going to show you here. So to create an expression, you go to Controls, Expressions, and you have this editor here. I'm going to create a new expression. I'm going to call it temp grad. So this is the temperature gradient. And I'm going to, there's a list of functions and things, but I happen to know what we got here, so I'm just going to do it. So I'm going to call gradient of temp. And this is going to be a vector output. I need to tell VisIt that. So now I have a new field that whenever I ask for it, VisIt's going to calculate on the fly. But I'm going to create another one real quick too. Temp grad mag. So I'm going to take the magnitude of that gradient. And you can, this is a little domain-specific language here, right? You can type arbitrarily complex things in here, but I'm keeping it simple for now. So we have our new variables. They don't exist in our database, but we can plot them now because VisIt's going to give them to us on the fly. The new ones are tempgrad, which is a vector, and tempgrad mag. Let's start with tempgrad mag since that's a scalar. We can find it here in our menu now. It appears. I hit apply. Let me get this guy out of the way. And this happens to be that magnitude of the gradient of temperature. Or we can take a look at this with a vector plot, which is a glyphing type plot for vector fields, and we can see our tempgrads here. I'm going to change a couple things on the vector plot. So the vector plot tries to be very conservative because glyphs can be expensive. So out of the gate, it just gives you 400. Well, that's probably too low. So usually we do things like a stride. We use like, say, show me every 7th one. And you'll see why. It can get busy. So let me go ahead and do that and draw. So here's our glyphs. And if I were to do stride 1, which might be okay for this data set, you can see there's just a lot of them. So usually you don't want to draw all of them. It just gets very visually complicated, right? But this is the glyphs that are showing here. You can change them, but it's showing you where that gradient is going, the vector field of that gradient, right? Okay. 4 out of 5 things done. So we got to talk about queries. So let's talk about queries. That's the last one. So I'm going to go ahead and just create our pressure plot again. And let me get us back to a wonderful view here. Now, queries allow you to do data summarization. So there's a lot of different ways to think about this, but basically anything you can do where you're taking big numbers and trying to get small numbers out of it, or you're taking things out and you're getting a different representation. Like a line out is technically a query. You're taking this mesh and you're getting this line back. The most basic of these, if we go to controls queries, and one of the most useful is there's like min and max queries, right? So I can find the minimum of a value and the maximum of a value in one click here. Again, there's a lot more, but I'm just going to show this one for now. So when we go into queries, we have options. The options for a lot of them are original data or actual data. What that is useful for is sometimes you've done something like a slice, and you'd like to know the answer of the query on the slice. Sometimes you'd like to know the answer of the query on the original data set, however it came out of the file. So this right here allows you to toggle between those two, but to reduce confusion, usually you keep actual clicked because that's what you're actually seeing, right? So when we hit query here, we get a bunch of information. So it says, hey, we queried pressure, the minimum's here, it's this node at this place, the maximum here, it's this node at this place. Other things you can do with queries are, there's a variable sum. So if you want to sum up all of our pressure, you can get the total amount of that. You can control these things with Python and stuff too, and that's what a lot of people do to do integrals and things of that nature. So, but queries are the last thing that we got. All right, now we're going to pivot to Python. So that's our next play here. So I'm going to go ahead and keep this open, but just switch gears a little bit here. So VisIt has a Python interface. It's had a Python interface for a very, very, very long time. One of the ways you can use it is you can use the manual. One of the ways you can use it is you can record things in the GUI, and that will tell you, the equivalent Python that you need to reproduce things. You can run VisIt without any windows at all, and you can hand it Python scripts. That's how we do a lot of our most advanced rendering, right? We get a job on a supercomputer, we say, go off, do this stuff, and then we come back and we get PNGs at the end of the day, or even data analysis results at the end of the day. Here I'm going to show you, I'm going to access it through what's called our command window, which is also where we do recording for macros, for Python macros. But I'm going to just be pasting stuff in to start, and then after that I will show you how to do the recording. So the command window is under Controls, Command, and I'm going to go through 2 examples here that show you some things that are similar to what I did manually going through this little whirlwind tour here, right? That's kind of small. Let's look at it over here. This is probably better. So the first example I'm going to show you, we have already opened our example.silo. We want to do what we've been doing. We want to make a pseudo color plot, right? We want to show something there, and then we're going to change some of the limits. So in the Python interface, this gives you an example of how things look. You ask to add plots, just like you would click add, right? You get the attributes of a particular plot, and then you make changes, just like you would open up the attributes window in the GUI, and then you would make changes, right? It's all very similar. In this case, we get a blank slate by deleting anything that happened to be there before. We add our pseudo color plot of temperature. We were doing pressure before, but we're doing temperature now. And we'd like to set the min and the max of this to another value and tell it to commit that. So if I go back to VisIt here, I have that script in our window. Let me try to get VisIt all the way up here. And I'm going to click execute. When I do that, it's going to pop up, basically it pops up our Python command line interface. So on Mac, it pops up in front of you. I could type Python in there if I want to. But here's the result, right? So we got our temperature plot. If I click here, if I go down to pseudo color, you see that these checkboxes were checked, and the values are equivalent to the Python. So that's good. That's our simplest example. Let's look at one that's a little bit more complicated. After we made plots, we want to do operators, right? So this is an operator example. One thing that's a little bit different about this is that we're scripting a bunch of different isosurface values. So we're just going to sweep a whole bunch of them. So you'll see it kind of animate as we run this. And in doing this, the takeaway here is, let me show it to you in here since it's easier to see, but you might. So we're adding our plot, we're adding our isosurface, and then what we're going to do is we're going to sweep over a whole bunch of values. And then that allows us to just think about it as taking our level set through a whole bunch of values. And if we wanted to, we could just say, hey, save each one of these, right, to a PNG. All we have to do is say save window. So let's look at it and let's watch it as it goes. So let me just execute. And you can see it's sweeping through the values. And this is a toy example, but it's shows you how you could do something. If you'd like to animate something not over time, if you'd like to animate something over any of the things that you could script with our attributes, you can do that. Finally, I'm going to show one more example, which is my favorite example, because I like to talk about the 5 building blocks of VisIt, and this one has all of them in it. Maybe next time I'll try to get lunch in there, but I don't think VisIt's going to be able to handle that. So what does this one do? So it adds our pseudo color plot of temperature. It adds a 3 slice, what we saw before. The goal here is we're going to do a pseudo color plot. We're going to create like a little diorama where our 3 slices is the background, and then we're going to vect streamlines and draw those streamlines. When we do the streamline stuff, we're going to use an expression to do that, to create that, like we did before, create the gradient and have that be an input to the streamlines. And then for good measure, we also do a query of the max here. So just show it to you real quick. So add a plot, add an operator, do our query, define vector expression. That's what I did before when I showed you how to create the gradient of temperature, right? But here I'm doing it in Python. And then we add another plot. This plot's special because it uses our integral curve operator, which is what we use to do streamlines. And it sets up options about where we're going to put the little ink, in the fluid and have it vect around. And we set some fancy style options here, right? So let me go back to our window. And let me just, oops, I executed that one again. I'll go to number 3, wait till that's done. All right, yells at me the first time, but when you try again, you will succeed. So here's our example. So we have that 3 sliced plot. Let me show you. So this is what it ended up creating here. So we have 2 plots. We have one that has the 3 slice and one that has our our streamlines in it, right? So, but this little script here, did all that stuff in a couple lines of code. So that's pretty cool. And then again, we can productize this and we can say run it without me looking at it, or run it every night, or whatever you want to do, right? There's a lot of power in that. Last thing I want to show you, Python scripting, and then we're going to switch over to the aneurysm tutorial, is how to record things and turn it into Python scripts. So our command window, which I was already showing you, I'm going to go to a tab that doesn't have anything in it here. So I have this blank tab, and I'm going to say record. If you just did this without the CLI being open, it would pop up in your face, but since I'm already using it, it's already hidden. You don't see that. Now anything I do here is going to be captured until I hit stop. So I'm going to go in here and let's go ahead and do what we've been doing over and over again. our pressure plot, for good measure, let's set this to something different so we can see that reflected. And you know what? I'm going to slice it too. Why not? I'm going to hit draw. And now I hit stop. Now, this is very verbose. However, it does replicate everything that you did, right? So in this case here, and there's a couple things that sneak in there based on me clicking and doing other things. But the takeaway you should think about this is this is a blueprint for you to follow. You can go in and say, well, this code's going to reproduce exactly what I did. You can look and cut out the things that you don't need. These are all the attributes of the pseudocolor plot. Well, if you look here, and over time you can learn these things, you'll notice that the ones, where's the ones? It's the min flag and the max flag are the ones that are actually mattered, and all the other ones are defaults, right? So you can go through and you can carve this down to be as simple as our original thing here, which is min flag and max flag, right? And experiment with that. And with this combination of building up the plots and playing with it, you can get, basically have these things and have them baked in and run them over and over and over again. All right, I'm going to take a pause and get a drink of water. So we're going to switch to the aneurysm data set now, and we'll go through some of that. I guess I could take like one question before we go to that. Give me a second to take a water if anyone wants to do that, or not, we can wait too. So, yeah.
So I was wondering for that mesh thing, is that adaptive? Like, for example, the resolution of data, if it has spatial resolution, does it know from that, or do we have to specify the mesh size?
So what VisIt's doing is VisIt is reading whatever data is published to it, and there's all kinds of different data that could be published to it, right? So from uniform grids like what you're talking about, which are evenly spaced, or unstructured grids, which could be arbitrarily complex. VisIt does have like a resample operator that will take any grid and turn it into a uniform grid by sampling at different points. So then you could say, well, hey, I have this complicated grid. Maybe I'd like to turn it into something simpler, and I want it to be 1,000 by 1,000 or what have you, right? And then you would have a uniform grid from that. And maybe you could save that to another file format or something like that. But VisIt it's doing whatever the data is presented to it, and it does have simple things and then all the way up to like block or patch-based AMR and all kinds of stuff, right? Yeah. All right, let's charge forward. Thanks for the question. So we're going to be doing the aneurysm tutorial now. So, and again, this is in the VisIt manual. If I skip steps or if you miss what I'm doing, you could try it again. And this leverages a data set that we got from some folks from Swiss Supercomputing Center a while ago. I'm going to open it up first. So this is was a separate download than the tutorial data, but it's called the aneurysm data. Inside this data set, we have an aneurysm.visit file. And then it actually has 200 different silo files that have 200 time steps of a simulation in them. All the VisIt file does is just group those 200 into one time series, so we can just take the time slider and drag. So I'm going to open that. Ooh, I'm still on Cooley. Why was I still on Cooley? Clever. All right, let's see. Actually, you know what? Just to make sure that things are A-okay, I'm just going to start over from the beginning here. So inside this data set, we have a mesh like we had before, and we have a couple different variables like we had before, although they're maybe a little bit more interesting because this isn't as much of a toy example. We have pressure, so the pressure is on the cells or the elements of it, and we have a velocity field. And this is a blood flow simulation, so the velocity evolves over time. It's not like a steady state thing. It's being driven by something. So we'll start by just looking at the mesh plot here. So I'm going to add a mesh plot and draw it. And then the first question we have here is, okay, so here's our little artery or what have we. We can see our mesh here. The first question is, okay, what type of elements do we think we're using here? This doesn't look like a uniform grid, right? What do folks think? What do you think these are?
STL probably.
Sorry, what was that?
An STL?
Well, no, it's not. It's a silo mesh. I'm wondering about the actual elements that are being used, like hexahedrons or tetrahedrons. There we go. Yeah. So these are actually tetrahedra, and so it's an unstructured mesh. That means you have explicit points in space and explicit connectivity that is provided to say where we have these tetrahedra. We can ask ourselves, we don't, this is a new data set, we don't know much about it. We can ask ourselves some questions with queries. So if I go to controls query, I can ask, say, how many zones are there? How many elements are there, right? And it'll tell me, oh, there's 100,000. Or I can ask how many nodes there are, because those tetrahedrons are defined on nodes, and there's a lot of shared nodes, as you would expect. I can go in and I can make this look prettier by changing mesh options, but we're going to do a little bit of that later anyway, so I'm going to skip that for now. But for now, we have our mesh plot. Another thing that we haven't seen before is this is a time-varying data set, so we have a time slider. Spoiler, the mesh doesn't change over time here, so this is a little bit of a boring plot here, or a boring thing here, right? So we looked at the mesh, we got tetrahedra, we've got this figured out. Next thing we want to do is actually take a look at some of the values that we have on one of the fields. So let's look at the pressure. I'm going to delete the mesh plot for now. I'm going to do pseudo color plot of pressure. I'm going to draw it. And now we have a picture here. We can see that there is a pressure, and it's not uniform, and we expect it to be evolving over time, right? So if I go ahead and drag our time slider, you'll see that yes, things are definitely changing here. So when you think about a blood flow simulation, or you think about something like this, you think there should be some sort of signal driving it, right? I mean, if you're doing a physically realistic simulation. So what would be driving it? Pressure. Well, but what would be the thing that you would be if you were modeling this? What would you have to think about? Yes, heartbeat, right? So if this is a simulation that's making sense about blood flow, there's probably some way we could think about the heartbeat, right? And maybe that signal is going to be there. How would we do that? We got 5 building blocks, so it's one of the 5. What do people think? How would we think about the heartbeat? How would we think about it coming out of this? Sorry.
You take a slice.
We could take a slice, but the heartbeats are like a 1D signal, right?
Apply pressure on the slice as a cyclic input.
Yeah. We could get this out of a slice. There's an easier way. And I'm going to tell you. Sorry. So we can do a query, right? I can say, this signal should be somewhere in my pressure, right? Maybe I just look at the pressure over all time. So we'll do that. So if I go to controls query, and I got to do something else right before I do this, I'm going to go to query over time options. So we're going to do a query over time, which means we're going to take a max across all the time steps. When I made this data set, I didn't put cycle data in it. Usually that's a metadata thing for a simulation. The time makes sense, but the cycle doesn't make sense. It's the same for all the time steps. So I have to go here and I have to say time is what I want my x-axis to be. And I'm going to come back to queries, which we saw before, and I'm going to do a max. Now this is a time varying data set, so we got a wonderful new option here. It says do time query. And this will allow you to read all the data sets and put them together in a big line, right? Since this is a relatively small data set, I can do all of them. But if it was a big data set, you might want to say do every 10th one. So there's options for that. So let me hit query. It's going to go off, and you can't see it. Maybe some of you can't see it, but it's working very hard for us to read all of those data sets, find the maximum pressure across all of them. And then we end up with this. Here's our signal, right? So this is the maximum pressure over time. You could also think about the minimum, right? There's a bunch of different ways you could do this, but we did manage to pull out something that looks like what we'd expect. And if you wanted to, you could go in and say, okay, what's the frequency of this, right? You can say, this makes sense. This is a human heart. This isn't another type of heart, right? We're just exploring this data set that you guys don't know, but as domain scientists using this data, the same type of thing apply. You figure out the right ways to use the tool to ask the questions that are important to you. So in addition to the pressure, we have a velocity field, right? Okay, so let's take a look at that. Let's switch gears and take a look at that. I already have my pseudo color plot. I'm going to go ahead and change here. Instead of the pressure, I'm going to change it to the velocity magnitude. VisIt automatically knows it's a vector field and defines this nice expression for me. I can click on this. And we know there's a lot of exciting things going on in this flow field, right? But luckily they're not on the boundaries of the mesh. We don't really want that. So except for the inlets and the outlets, right? So if we start doing this, we're back to where we were before, where it's like we know there's exciting things happening, but we can't see a lot of it. I mean, if you see me going over time, you can see that things are happening here, but I'm missing a lot, right? So what can we do? Well, if we're going to look at the structure of the field, in this case, the magnitude of the vector field, we can use isosurfaces, right? We can use contours. So let's do that real quick. So I'm going to go down to slicing, which we did before. Let's say slice. Oops, that's not what I want to do. I'm going to go down to slicing and do isosurface, sorry. And I'm going to put some values that I know happen to be where things are moving fast. So this is just, you know, in terms of the units and stuff, I don't completely know what they are, right? But I know this happens to be where the fast things are happening. So the isosurfaces we're going to see are things where there's a lot of flow. So I'm doing 10, 15, and 20. And I'm going to hit draw. And now we can see we have these, these tubes that appear, and they kind of, over time, they come in and out as the simulation's driving. So remember, we saw our heartbeat. Well, this makes sense, right? So we have a pulse. So we have a lot of movement. Then we have like a stagnation. And then we have another lot of movement right at the end. The only problem with this is that these could be like worms in a galaxy far, far away, right? We've lost a lot of context here. We know we were looking at blood flow, so we're going to go ahead and try to bring some of that context back. One way we can do that is we can add another plot that just shows us kind of the boundary of our data set. And the first thing I need to do before I do that is we don't want to take our isosurface of this plot that I'm about to use because it'll turn back into these worms in another galaxy. So I'm going to uncheck this thing here that says apply operators to all plots. And then I'm going to add a new plot. I'm going to use a plot we haven't used before. It's called the subset plot, but it's kind of like the mesh plot. You could do the same thing with the mesh plot here, except it only shows whole parts of a mesh. So I'm going to do a subset of, say, domains or mesh. Either one would be the same in this case. And I'm going to pull up the attributes here. And what I'm going to do is it's going to color it a solid color. So I'm going to select this blue, and I'm going to pop it down to like 25% opacity. Hit apply. And now I hit draw. And now we got our two plots, and we have some context, right? So we know what's going on here. So I can now look through over time, and I can see, okay, well, here's where things are happening, right? And they match what we'd expect. And you can see where the problems might be happening and where things are happening in terms of the nature of the vector field. We're not directly drawing the vector field here. We will. But this is all just using those isosurfaces on the magnitude of that vector field. Another thing I want to point out is isosurface is a nice way, but you might not always know. Isosurface is a level set at a precise place, a surface in this value. You might want to sweep a volume instead. So if you look in here, you can see we got a lot of stuff going on here, but ultimately it's really a couple different surfaces, right? We know those surfaces are at 10, 15, and 20. But what if we cared about the structure where everything is moving fast? We can do that with an isovolume operator. So I'm going to remove, actually I'm not going to remove, I'm going to have both of them here so we can compare them. So I'm going to add a new pseudo color plot of our velocity magnitude. And I'm going to add an isosurface operator. That's under selection because it's not actually slicing, it's taking a subset volume. And in the isosurface operator, instead of telling it 3 points in that field that we want, we're going to tell it we want everything between 10 and 20. I'm going to hit draw. So now you'll see that we have this volume here. So this is really powerful. Now we can extract volumes from based on how the fields are. And if we look here, I'm a little crunch for space, but let me try to. If we look here, we can flip back between the two. So what I did is I hid the first plot and then I selected both of them. And now I can kind of flip back and forth, show you the difference between the two. So the nice thing about an isovolume is you could integrate it over the volume, right? You could find mass of an isovolume. You can't really do that with the isosurface, right? You're just stuck. You could do surface area, but you can't do a mass in that way. So this is great. We've gotten pretty far. We're understanding things pretty well, all without looking at the velocity vector field itself, like plotting it directly. But we can do that as well. So what we're going to do here I'm going to delete these guys, and I'm going to keep our background so we have the context there. So I have just this subset plot mesh. And I'm going to add a vector field. So the vector field is going to show me glyphs directly of the vector field of the flow that we got going on here. There's a lot of options for this. Again, we saw it before. VisIt tries to be conservative, but we want to do something a little bit more, so we want to draw every fifth one. I'm going to do a couple other things. I'm going to go into data, and I'm going to change a different color table. Oops, I don't want that one. And I'm going to scale the glyphs by a number that I know makes sense. You can also make them fancier, so I can have a cylinder, and I can have high quality geometry. So again, glyphs are making all this geometry to represent this, so all these things have some cost. Usually you dial them up to super nice when you're happy with what you got, how you've set things up. All right, so here we are. So now we're looking at the vector field, and you could probably tell me that maybe, Cyrus, you shouldn't have gone so crazy with that scale, but that's okay, it changes over time. But now we can see how the flow changes, and we can animate this, and we can see where things are going really fast over time, right? And if you wanted to, you could save a movie out for this. Still, I think we can go further. So this is the instantaneous view of what's going on here with the vector field, right? We can ask questions like, well, what if something started down here? Where would it be after a certain amount of time? You can do that with something called path lines. So streamlines will tell you if this was a steady state simulation, if this wasn't moving, given the vector field you have now, if you had vectored it to infinity, or if you had vectored it to some start point, where it would go. But path lines can actually read every time step and say, okay, we're gonna move, the vector field changes every time step. We're gonna move particles a little bit, then move them a little bit more, and move them a little bit more, and we're going to take that all into consideration. So what I want to do is I want to show you the streamline case first, and then we'll finish with the pathline case. The pathline case will be, at the beginning of the simulation, if you started here at the bottom right, where seeds would appear. And then the streamline case is going to be, if you pretended like each part of the simulation was at steady state, where they would go. So, okay, good. But to do streamlines or pathlines, I got to select where to put them, right? So we're interested down here because that looks like where things are starting. But do I know where that is? I do, because I've cheated many times with this, right? But you might not know, right? You might want to use some of VisIt's tools to actually figure out where you want to set something up. So we'll do that real quick. What I'm going to do is, I don't know exactly where this thing is here. But it looks like it's at, what, x equals 3 or something like that, right? So what I can do is I can do a slice at like x equals 3, and I can take a query, and the query will tell me where the maximum value is in that slice plane. So let me do that here. So I'm going to add our pressure, and I'm going to add a slice. And I do have to cheat because I need to know. So we said we're going to do it around 3, so we're actually going to do this at an origin of, let's see here. Yeah, so I think I'm going to do it at 3, 3, 3. Let's go ahead and draw. Oh. Yeah, and I have to uncheck this project to 2D, or else it's going to yell at me. It's saying, hey, you created a 2D plot and a 3D plot, and I don't want to draw those together. But there we go. We got our slice down here, and it's we actually have the pressure field on there too, although it's set to really high, so it's a little bit strange. It looks a little bit strange, but we have that there. So we can go ahead and let's change this to velocity. I think that's probably what it should have been. Yeah, there we go. That looks a little bit better. So there's our velocity. We can see that things are moving a little bit faster on the inside. And if I go here and I say controls query, so again, using the tools in our toolbox, and I ask for the max, I get, here it is. It's at 3.4, 3, and 5.5. Great. So I can use that information now to set up a streamline plot. I'm going to do it quick because I only have a couple minutes. But the way you do that is you go to start. It's going to be a pseudo color. We're going to still be drawing something here. But we're going to use operators, integral curve, and we're going to do an integral curve of the velocity. There's a lot of things to do here. Setting up streamlines, there's a lot of choices, much like volume rendering. There's a lot of things to think about. The most important thing is where you're actually putting the starting points, and we already figured that out, right? What do we want to do? Well, let's create a circle around the bottom here. Let's go ahead and set it to be on the boundary of this circle. I'm going to set this to be 12 different samples, so I'm going to have 12 seed points. The radius is important because if I get it too big, it's going to be outside the data set. So I happen to know 0.12 is fine. And then there's a couple other things you still have to think about. So which way's up, all these things. And I'm just going to dial those in real quick. Another thing I'm going to do is there's a bunch of warnings that VisIt provides, and they're useful, not in a tutorial context. But we're advecting particles here, so there could be bad numerics happening. These tell you about when things happen, but we're going to turn them off for now. I'm going to hit draw. Oops, what did I do? Oh no. I know what I did. I didn't put in the right origin. So we got our 3.45, our 3, and our 5.5. And then I needed to fix this normal. Yeah, sorry. There we go. So they're pretty faint. We can go into our options here and make them look better by saying, hey, I want tubes and I want tails. Oops, and I want tails and heads to be like little arrows. So there's a bunch of things you can do here to make it look a little bit fancier. So we just do that, but we can see it now. So now we have our streamlines, and again, this is still viewing them instantaneously. So if you look at this between time steps, things change wildly. But right now with streamlines, we're pretending like each vector field is like a steady state solution and just saying integrate to infinity. To do the path lines, what we need to do is we need to start at the beginning of time, because that's what we care about. And we go into the integral curve operations, and we can switch here to path lines. Only other thing I want to say about this is that important option here is we have this mesh static over time or mesh changes over time. What we have to do is we basically have to interpolate these vector fields between time in order to figure this out. So the general case is things change over time, and VisIt can handle that. Super expensive. If you have a mesh like we have that's not moving, then we want to just say, no, it's the same, and then we can just difference fields. So if I activate this and then hit apply, VisIt's back to doing its thing, where it's reading all 200 files for us, thinking hard. And here we end up with our answer. So this is the answer if you were to seed things at the beginning of this simulation. Here's how it would flow through by the time of the end. And that's where I'm going to stop. So the purpose of this is to kind of show you how to put the tools together and think about things. I guess I'll take questions, but I'll also be around this afternoon, and you have to hear a little bit more from me on another time, so I don't want to use too much time. But just quickly a question, I guess I'll unplug so that the next speaker can get set up. We good? Because I think we're at time, right? Yeah, we're done. Yeah, time. Yes.
So in some data sets, like the velocities are defined as scalars, like Vx, Vy, Vz instead of a vector. So can I combine these three and define a vector? How do I do that?
Yeah, you can do that with the expression infrastructure. I showed you the opposite, right? I took a vector and turned a magnitude. You can just say, you basically do braces and you say x, y, and z become a vector. I can show you how to do it if you need, yeah. Any other questions? Yeah.
Python scripting do you guys have any database with sort of template scripts for if you want to do simple things like slicing, for example, or is that not really something you provide?
We do have a manual that shows a lot of different things, and then the tutorial shows a couple things. I think the thing to learn is you do that record thing, and that unlocks everything, right? So I think just spend a little time playing with that, and then that can help you distill your own scripts. But there is a really long manual if you want to read it.